We have now talked about rules of inference, and we have shown many of these rules, but one thing that is kind of missing is we didn't have anything on quantified statements other than we treat them just as a proposition, but a quantified statement could be way more complicated than then our previous rules of inference will not do much good for us. So I want to start with an example, perhaps a very simple example. Let's say it's example 12 in the book, if you want to look at it more. But it says the following: if everyone in this class has taken computer science course. Let's say that was a prerequisite. So everyone in this class took a computer science course. And the second statement is Marla, just a name, is a student in this class. Now what we want to conclude is that Marla has taken a computer. So to prove, or to conclude, if you want, Marla took a computer science course. Now that seems quite obvious from if you just think of it in general English, but how does it work formally? And that's the little bit the question here. Now, so what is coming on here is that we have a quantification. Everyone, remember that's one way of saying a universal quantifier. So for all students in this class, they took a computer science course. So we see that we have here a variable x. So here x are the students in this class. I take that as to be my domain. Now you could say, why don't you take that as domain all the students in the college and then take a predicate saying that they're in this class? Yes, I could do that too, but it is kind of oh no, sorry, that's what I should do. Sorry, x is a student. Yeah, sorry, I said, why didn't I do this? Well, it's because I need to do it. So x are students, and then we have a predicate, let's call dx, the predicate x is a student in this class, in the discrete math class. And then cx is now, so here, if you see here, this is either to be in this class, that's a statement made about the student, and then also a statement made about the student is taking a CS course, so x took a computer science course. Okay, so we have predicates that talk about certain objects that are range over whatever domain that we are working on, in this case the students of this college or whatever. Okay, but we also have something else. We have a concrete student. Marla is a concrete student, so it's one of these possibilities for this x. Now let's see, what does the first statement say? The first statement says it's a universal for all x. If you're in this class, you have taken a computer science course. That's a universal statement, right? Now again, you say, well, why do you put an implication? I don't see it. Everyone in this class took a CS course. There's no if-then, right? In English, we very often avoid that by making statements like this. But suppose, so how do we figure this out, how to write this formally, right? So you might think, well, I would have said dx and cx, right? Everybody in this course has taken a computer science course, but what are you saying really? Now, remember, this is wrong, right? So why is this wrong? What is it actually says? It says for all students, they have taken this course and they have taken computer science courses, way stronger than the original statement was. So this is definitely not it. So how do you know which one it is? Well, you could try to rephrase it. So everyone in this class took a CS course. What does this mean? That means that if a student was in this class, then he took a CS course. Look, just reformulating it in a very direct way gets me the if-then. So if you're in this class, then you took a CS course. Okay. Now the second statement is Marla is a student in this class. So this is actually just a statement about Marla. So the Marla. Okay. Now, well, all rules of both are propositions, right? The first one is a quantified statement, so it's a proposition. It's true or false, and we'll be assuming it's true now. And so is the second one. Both are now assumed to be true, right? So how do I deduce from this that Marla took a computer science course? Formally, if you look at all the rules that we have so far, none of these apply to it. And so there is now a new rule that we're going to use, and I'll discuss all the variations of this rule, and this is called, in this particular case, universal instantiation. Universal instantiation. Mouthful, but what does it mean? It means that if you're making a universal statement, in other words, if you're saying for all, then you can apply, you can replace the variable x by any choice you make. This means replace x by a concrete choice. Well, concrete, perhaps I should be careful when I say concrete, because sometimes we have to say, okay, there is a certain guy, but we exactly don't know his name, but we call him Mr. X. Well, okay, that's not a good thing because X was our variable, but by a concrete choice. So perhaps I'm going to put a concrete limit between parentheses, because you see in the discussions later, we'll see that it's not always very concrete, but okay. That's universal instantiation. So what does it say, therefore? What's the rule? So let me write it up here. So for all x dx, then cx. So what is it in general? Perhaps before I apply it to this general thing, so what is the general rule of universal instantiation? So I'm going to do this for an arbitrary predicate, not the particular one that we have. So for all x px, so this is, I'm now telling you what universal instantiation is. That's the rule. If you have any predicate p, and we are in this situation because, remember, we have the d and c in the previous example are like elementary predicates, but we know that we can build more complicated predicates by using the rules of logic, by ands and ors and implications and so on, and negation. Okay, so what does the universal instantiation rule say? Well, if you have for all x px, then you can conclude PA where a is in the domain. That is the concrete choice, if you want. Well, how concrete, that depends a little bit, but it is an instance of x, an instantiation, and it's a universal instantiation. You will see we'll also have the other existential instantiation. So for all x px means where a is anyone in the domain. It doesn't matter who I take, I can take anyone. How can I apply this to our particular our setup here? Well, I'm going to do this apply this to this universal statement. And so what it boils down to is, if you do universal instantiation, so universal instantiation, I'm going to write it this way, that means that you replace x by some a. Now, I have a particular a in mind because I want to talk about Marla. So I can replace x, so what I do here is x, replace that by Marla. Of course, there's no quantifier anymore, so I have d of Marla implies c of Marla. I remind you that if you have a predicate and here's a variable, you can replace this variable by one of the objects in your domain, and here Marla is one of the objects. So C Marla is either true or false. The same for D Marla. Now, so that's the universal instantiation. But now I'm going, right, because I also know this D Marla, so I know this to be true. So we have an implication of which the hypothesis is true. Then we can conclude the conclusion, and this is what we call modus ponens. So as always, whenever you use one of these rules, please put what the rule is that you use. Okay, so now you say, let's see, what was it? The proof is Marla took a CS course. That is, we achieved the goal. But let's put it even No, that's good. That's good. That's good. No, no. Let's do a second example, perhaps. Let's take one example at a time. So here is another example, building on the same thing. So I have still dx is a student in the class. Now bx is the predicate to read the book. X read the book, or bought the book perhaps, or has the book, right? So the students I want to make is this: a student in this class has not read. A student in this class has not read the book. Everyone in this class passed the first exam. So let's put f of x. X passed the first exam, the first quiz, because we don't have exams. So let's make it the first quiz. Okay. So these are now all my predicates, and the two statements I have: a student in this class has not read the book, and everyone in this class passed the first exam, are now two things that I can write down formally using these elementary or these direct predicates D, B, and F. Now what I want to show is to prove someone who passed the first quiz did not read the book. So from this information, this is what we want to derive. Okay, so as always, the first thing we should do is, well, we have already named our predicates. I call that step 1. Step 2 is now writing down the statements. And let's say that a student in this class has not read the book. What kind of statement is that? Again, you have to be thinking English has very many ways of saying the same thing. And so if you rephrase this a bit, it means that, well, there is a student that has not read the book in this class. There is a student, so existential. There is an X. Now, what do we have? There is a student in this class, so there is an X. The student is in this class, but he has not read the book. This is now what it says, right? It's not that if you're in this class you haven't read the book. That's not what it says, so there's not an implication now. Now there's a real end. A student in this class has not read the book. There is a student in this class. There is a student who is in this class and has not read the book. There's an and here. So that's the first statement. The second statement was everyone in this class passed the first exam. So that's much more obvious, I guess. For all X, if you're in this class, you passed the first exam. Again, there is no if-then, but I hope that, okay, sorry, everyone in this class passed the first exam. There is no implication here, so, but it is not an and that we want to say. What we want to say, everyone is in this class and has passed the first exam. You say, well, this is true now, because you said everyone in this class has passed the first exam. Yeah, but I didn't claim that everybody is in this class. There's a lot of people, well, normally you would see a lot of people hanging around on the hallways, but okay, anyway, you know that there are a lot of other students in this college, so not everybody took this class, so you cannot put an end here. It is an implication. Why? Well, if you reformulate it, everyone in this class passed the first exam, that means that if you're in this class, then you passed the first exam. Again, an if-then. And that's the two statements. So step 3 is formulating what we need to prove. We need to prove someone who passed the first quiz did not read the book. Now, what is this? Someone is, let's again rephrase this. That means that we have to show that there is somebody, you hear the existential quantifier, who passed the first quiz but not read the book. So there is an X, Fx, and not Bx. Again, it's an and here. It's the person passed the quiz but did not read the book. We say a but because there is a not coming. But it really is an and. It's weird if we say it, but if in English, if we would read the sentence that I just now formally wrote down, it says there is a student, and the student passed the class and did not read the book. Okay, we feel that we should put a but there, but that's just what, because we think about the content. But this formal logic is separate from the content. It is applies to anything. Whatever statements you make, as long as you're making valid statements, you get valid conclusions. That is what formal logic, that's the promise of formal logic, no matter what these things actually mean. Okay, so this is what we need to prove, and this is what we have. Okay, so now another thing we need is the rule of we know that we can do something with this guy here, right? We have now this principle, what we call universal instantiation, but I have no clue to whom should I take here. So better perhaps look at this one, because this says there is a person, perhaps the person that it is talking about, that's the guy that I want to find. So let's look about this one. So this says there is a guy such that this is true. He is in the class and has not read the book. So what we need is a principle, the principle of existential instantiation. Instantiation, I'm probably writing it wrong, but okay. So what does that say? That is, if you have an existential sentence, statement, proposition, where P is most likely a complicated predicate about this x, this variable x that lives in a certain domain, then what can you conclude? PA holds for some A in the domain. It doesn't say which one, it doesn't give a particular name, but it says there is some A in the domain. It looks very similar to what we had here, this here, where A is in the domain. I should have perhaps even better said for where A is any choice of person in this domain. So this A could be anyone. This A is someone which we perhaps know or perhaps we don't know. In this particular case, that we have no real concrete information. They don't tell us. Look, the difference here is that we're not getting told that Marla is in this class and has not read the book. So there is some guy, but we don't know, is it Marla or is it John or whoever it is. Okay, so this is the difference, but again, it's an instantiation, right? We replace x by some value of A. Good. Are we done? Well, no, because okay, sorry. This is the general principle. Now let's apply this to the one we have here. Sorry about this one. So we have there is an x dx and not bx, and so at this point I don't need to know anymore what. That's the whole point what I was trying to make about formal logic. Whatever the content of D and B is, I don't need to know. I'm just using my rules of inference. That's the strength of this formal logic. Okay, so I now know that I can instantiate this. So I'm doing existential instantiation. So existential instantiation tells me dA and not BA for some student A. Some A, student A, some A, let me just say some A. So there's some student A that satisfies these two things. Now what I'm trying to go is, let's see, what I'm going for is something, there should be some student, there's an X, such that we have this. Now, okay, we have this already, but we don't have that yet. About this particular A satisfies this, but does this particular A satisfy that? Well, of course, now comes our second one. So, and what are we going to do for the second one? I hope by now it is clear. Try to figure, again, anytime you think, oh, I think I know what to do, try, stop the movie, pause it, look at it, and see what it is, how far you got. So, for all x, dx, then, what was it, fx. So now, by the rule of universal instantiation, the one that we talked about previously, right? Universal instantiation. That means, okay, now I can put here I can replace x by whomever I want, but I'm going to replace it by this particular A. That's the whole clue. It doesn't help me if I take here for A to be Marla. Sure, I get some information. I know that Marla is in this class. If Marla is in this class, then she has, what is F again? passed the first test, I guess. Yeah, first the quiz. But I don't need to know this at the moment. So I'm going to not use Marla. I'm going to use the A that I got from the previous statement. And therefore, it was important that I did the first, I dealt with the existential one first. So I do DA, then FA. Okay, but what now? Okay, we know that. Remember, keep always an eye on the price, right? Where we're going for, we have to have something about F here. Okay, that's good. That's a conclusion of an implication. So I need this DA. Do I have that? Well, I have this. But there is a rule here that the rule that DA and not BA, if we have a statement that is, if we have a conjunction, that we know that any of the two conjuncts must be true. This had a name, and in the textbook they call this simplification. I would just, this one is so obvious that I kind of just, but it is a step of a rule of inference, so you have to show the rule of inference, but this I don't give, you normally don't need to give a name here, but I'll write it so that you can double check. It's called simplification. Simplification, which is, if you ask me, a stupid name, because simplification is something that is used 700,000 times in mathematics, right? So what is that? Doesn't give you much information. Okay, but you see it's a true statement, right? If you have one thing and another thing both are true, well, then at least the first thing is true. The same for the second thing, right? So we have now DA. I am now in good shape because, right? So this one I got from, sorry, here, and now I'm using this one here. I'm making these arrows to show that I'm constantly using things that I have proven to be true, right? Everything that whenever I have this symbol here, I can conclude, means that it gives me a new truth. So I'm gathering truths. I'm putting all these, making a list of I'm making a list of different true statements, and hopefully in that list eventually will appear the statement that I'm trying to prove. We'll talk about it soon, and we will call a coherent list of true statements that leads to a conclusion. We will call that a proof, obviously. Okay, so let's go back to where we are. We have this here. We know what to do this. We have an implication, and we know the hypothesis is true, so we do modus ponens. And so modus ponens tells us that now f of a is true. Good. Let's go back to where we are. We wanted f. Yeah, that's good. I know f of a. I also know, by the way, well, I know this one, but therefore I definitely also know this one by the same simplification rule. So perhaps I should do that, right? So I now going to use one more time. Well, okay, I can shave some space here and conclude two things. It's very common to do that. That if you can conclude two things, to separate them by a comma, meaning. So what I'm trying to say here is, if I know that a conjunct is true, then any of the conjunction is true, then any of the conjuncts is true. Okay, so I have now this, I have now this. Now I can put them together. So I have this, right? These are two, this if you want, this comes, this I just had proven here. We can put them together, and that is then called a conjunction, right? We make a conjunction of that. We have FA and not BA. So this is a new rule of inference, which is called conjunction, because that's what we're doing. In other words, it says that if you have two true statements, you can put them together in one single true statement by putting an and in between them. Okay? Yeah. We seem to be getting where we want, right? Where is it? This is what we want. Let me put a color it. I kind of have it, except I have a particular A here, and here this is a quantified statement, and this is just a proposition. And this is the next thing that we need to set there some several rules. So now is the rule of existential generalization. Wait, that's the name they use, right? Because they sometimes, yeah, okay, existential generalization. But is this rule say? That says that if you have a predicate that holds for some A in the domain, then you can conclude the obvious thing that there is an X such that Px. it's really not a rule of inference. It's more like, what's the meaning of this existential quantifier? That's exactly the meaning of this existential quantifier, right? If you know that the predicate is true for some witness, if you have a witness, as we call that, then you know that the existential statement is true. But okay, it is a rule, and it's called existential generalization. So that's what we're going to apply to this guy here. So we have FA and not BA. So what is the difference between instantiation and generalization is now that we replace A by X, but of course we have to add a quantifier plus a quantifier. Okay, so okay, the quantifier is there is an X, and now I can replace A by X. And this is exactly what I wanted. So you might guess there is still one rule missing. I'm not going to do a problem with it. This is for the homeworks. That is universal generalization. That is, so you could think of this generalization rule, the existential generalization. You can think of this existential generalization as a way of generating an existential or proving an existential statement. How do you prove a universal statement? Okay, so it's kind of the same thing, but it's subtle. PA holds for all A. If you can show PA for every single A in the domain, you go to Marla, and then you take John, and you take Juan, and you take some other person, you go over everybody, you finally establish that it is true for any of these guys, then you can conclude for all X, Px. So as I said, we replace A by X and a quantifier. And so that's why we can do as well an existential quantifier and a universal quantifier. But of course, it depends on the information. Here we had some, here we had all. That's the difference. Okay, that's our rules of involving quantified formulas, quantified propositions. So. And I'm gonna show a couple of homeworks again. We will do a quiz also on this type because it's slightly different, and it's something that I want you to know, because it is kind of the basis of all mathematics. Not so much as of mathematics what it produces, but mathematics how it works. Because when you do, I'm a mathematician, meaning I'm a scholar, a researcher. What do I do? Well, I present a result, but just telling everybody, "Hi guys, I found this, and if you don't believe me, well, too bad for you." That's not how it works. What I have to do is I make this statement that is producing mathematics, make a new result, but then my peers are coming and knocking on my door and say, "Hey, how did you get this? Are you sure this is true? Show us." And then I have to give a proof. So if you look at any publication of researchers, you can browse my webpage and check it out there. There are many papers in there. You see that it constantly is giving some new ideas and new formulation and making some statements, theorems we call them. So theorems are statements about some objects that we are interested in that are somehow novel, in the sense that it was not something that was clear from the beginning. That's what we call a theorem. But then if you look at what the bulk of the text, if you would count the percent of text in an article, you see the bulk is the proof of that result. Depends a bit on the type of mathematics, I should say. I'm talking here now about abstract mathematics. Now we are in a technical college, so many of my colleagues are actually applied mathematicians, where there's a different form of mathematics, as valid and as correct as the mathematics I'm talking about, but it will be more calculation and less proof. And that is perhaps something that you always thought mathematics was. Mathematics is calculation. No, most of mathematics is actually proofs. So if that's the case, and if you guys are taking a higher math course, there are going to be proofs, right? And so that's my segue into the next topic, is introduction to proofs. Now I'm going to split this into two parts. And the first part, what I'm now going to do is basically almost what I just said here, except I'll give you some examples of proofs. But in the next video, I'm going to do a very important proof technique, which is called proof by contradiction. It's a weird technique, and so you have to get used to it. Now, we know already what proofs are because you have learned about proofs by induction. And okay, so no, we have no. Sorry, no. Apologize. I'm teaching discrete math 2, and of course those guys know proof induction. This is something we will talk at the end of the course. But so now in an introduction to proofs. So I'm gonna, and what often the most statements that you will see in mathematics are implications. Okay, and they said if something, if this and this and this is true, then also this is true. That is what we mostly do. Okay. Of course, there are statements that are not like that. For instance, the statement 17 is a prime number. Okay, that is a statement that doesn't involve anything. But for instance, if you look at, if you must have perhaps heard about this, although this happened a bit before your time, I think, or when you were interested in Lego blocks more than in mathematics. Fermat's last theorem said the following. It said that that if you he said it for x to the n plus y to the n is z to the n has no solutions. If n is bigger than 2. If n is 2, there are solutions, because it's 3 square plus 4 square, that is 5 square. That is very well-known identity, property of the numbers 9, 16, and 25, right? If you're working with Pythagorean theorem, that always, most of these triangles always have size 3 and 4 because that they have this nice property if you have a right triangle. So this is for n. If n is 2, we have solutions, like we have things like this. But if n is bigger than 2, we have no solutions. I should be more correct by saying no solutions consisting of natural numbers or even integers. There are no integer solutions. There has no integer solutions. And even that is not entirely true, because I could take a stupid solution, let's say for n is, so n is 3 was the first case, and in fact Fermat himself proved it for n is 3. So for instance, 1 cubed plus 0 cubed is 1 cubed. So actually there was a solution, so that has no integer, what we call non-trivial solutions, or non-zero, has no integer non-zero solutions. Because 0 is kind of a silly thing, so let's not talk about this particular one. So, but in other words, you can never have one cube and another cube, you add them up, it's also a cube. That is not possible. And this is called Fermat's last theorem. Now, as I said, so the first here, if you look at this line here, this is a statement that is, you could make this a mathematical theorem, right? 3 squared plus 4 squared is 5 squared. It is correct, and therefore it's a theorem, because, but that's a theorem supposed to be. It's a statement that is true. So it is a theory, but it's a very uninteresting theory. Okay, what you could conclude from that, there are x, y, and z, such that x squared plus y squared equals z squared. It's a little bit more interesting result, because okay, if you would give this to say a second grader and say find me 2 squares that add up to a square, it might take some while before he has found that. And again, I'm always assuming non-zero here, right? There are non-zero x and y's and z's. So how did I get from this to there? Well, we just discussed this, right? This is called existential generalization. Now, when we talked about it in existential generalization, instantiation, where is it? Here it is. Let me color it. We had one variable, but I hope you can be flexible and say that you can do this for every variable. And you can even mix and match. You can take the first variable you do in universal generalization, and the other one you do existential, and so on. But okay, here we're going to just do, we have a specific solution for x, for y, and for z. So there is some x namely 3, there's some y, namely 4, and there's some z, namely 5, such that this is true, so I can now go to use existential generalization, and I get a theorem. Well, not very much. Now, what is this then? You say, well, what if the statement is this? Well, here, when we say this, there is no integral solution, but we say basically for all x, x to the n plus y to the n, for all x, y, and z, sorry, x to n plus y to n is not equal to z to the n. Okay, that's what it means. Now, this is not an implication. I said most theorems are implications, but this is an example of something that is not an implication. In some sense, it is, because I have to exclude the fact that x and y and z are 0. But okay. So for all x, y, and z, x plus 1 plus y and 1 is not equal to z to the n. Notice that when you Fermat's theorem says something like that, it makes a statement without really quantifying. Okay, and that is something one often has to do. So I want to give you an example of something where we don't quantify. So here's the statement. A typical statement that you would see all the time in mathematics. If x is bigger than y, x and y are positive numbers. I'll just give this as a... Then x squared is bigger than y squared. Now, this is a true statement, you would say. Well, be careful. It actually is it's not a statement, it's a predicate. It's a predicate that contains two variables, x and y. So how can a predicate be true? That's not possible, right? A predicate is only true if I plug in things. Yet, in mathematics textbooks and so, you will see constantly these things: if x is bigger than y, then x squared is bigger than y squared, and that is being claimed to be a true statement. But then, I can repeat, it's not a statement, it's not a proposition, because there are variables. So what is actually meant? When we write this, we really mean for all x and y, pxy. So, in other words, there is an implied universal quantification. And this is also something that is, it's basically mathematicians or textbook writers or anybody being a bit lazy, right? And so when a statement is made where x and y are very general things, right? Of course, if I write if 2 is bigger than 4, then 4 is bigger than 16. Well, first of all, good question. Is this a true or false statement? How many of you thought it was false? Well, it was true. Why is it true? Remember, if an implication is only way that an implication can be false is if the hypothesis is true, but the conclusion is false. The hypothesis is not even true. So this is a true statement. I know, this is something you could protest about as much as you want, but this is how it worked. This is how we made the truth tables. If 2 is bigger than 4, then 4 is bigger than 16. But 2 is not bigger than 4, so what does it matter? Right? If you don't believe this, remember that the statement P then Q is logically equivalent with the statement not Q then not P, the contrapositive. And now, what is the negation of 4 is bigger than 16? 4 is less than 16. If 4 is less, so this would mean if 4 is less than or equal to 16, then not P, then 2 is less than or equal to 4. I'm taking negations. And this is a true statement now, right? So if this is a true statement and this is logically equivalent to that, so it better also be true. Okay, so first lesson therefore was if you see a statement like that, we have often there's a universal quantifier meant. So I want to give one example of this. Say, prove the following. If n is odd, then n squared is odd. So again, this is considered to be a theorem. And that's a textbook. Textbooks can have these as theorems. But what we really mean, so we really mean if for all n odd, then n squared odd. I'm not writing it fully as a predicate that sometimes we do like these. I should have written it odd. Okay, let's make a predicate out of it. Okay, before you mumble and protest. alt n. Okay, let me rewrite the whole thing. So I'm going to have a predicate alt x means x is odd, and then I say alt x implies alt x square. That is really the statement for all x. Well, for all n, of course, I can name my variables whatever I want. So, okay, let's stick to the name that we had. Oh, okay, let me take x so that you see we can be flexible here. Now, the one thing, of course, that is also never mentioned, as I said, in universal quantifier is not even there in the original statement. Another thing that's not in the original statement is what is n actually. And here, n is supposed to be an integer. Of course, because otherwise it doesn't even make sense to say what is odd. You cannot say what when a fraction is odd or when is pi odd or is pi even. That doesn't make sense. So, and therefore if I quantify and I write for all x, I mean for all x for which this statement is supposed to be true, namely for all integers x. Odd x implies odd x squared. And I hope that you agree that you can use predicates, not just one letters but several letters makes it much more legible also. Okay. So how do we prove now such a thing? Well, that's the thing. I go back to when is an implication true? Well, there are many. If the assumption is false, then the implication is automatically true. So if I want to prove that an implication is true, I don't have to worry about the hypothesis being wrong, because then it is true anyway. So there's nothing to prove there. I'm trying to prove this implication, right? So the only case that I have to verify is, if you think about the truth table, right? In the truth table, there are four possibilities. The predicate, the hypothesis could be true or false, or the implication could be true or false. But if you look at that, there's only one that I have to worry about, namely that if my hypothesis is true, then also my conclusion should be true. So a typical proof would be, therefore, in order to do this, so proof, how does a proof work? Well, suppose n is odd. This means we're taking a witness to this hypothesis. So what we're actually doing here is a form of universal generalization, universal instantiation. We have to prove for all x. What we're going to do is we're going to take an arbitrary n. So n is some number that I have not specified, except that I know that it is odd. And then I'm going to prove that n squared is also odd. Okay. So this is the direct proof. So suppose n is odd, to show n squared is odd. That's how we prove work. I'm sure that that's what you would do if you're asked before I started explaining this, but I'm trying to explain the logic behind it. Now, this particular thing, how do we prove this? Well, it's sometimes these predicates in mathematics, they replace some, they have some particular meanings. So we have to better understand this meaning. What does it mean to be odd? Well, it means to be not even. So let's call even x. X is even. And then we know that odd x is the same, is logic equivalent, or is the same as not even x. So, okay, if I want to talk about odd x, perhaps I should also say what even x is. Even, okay, so what does it mean x is even x? Well, it means what? That it is a multiple of 2. It means there is a k such that n is 2k. So in some sense, this predicate itself is a quantified statement with a new variable k. Okay, understand that, right? Because to say that x is even, sorry, x, my variable is x, so I should call it x here. So notice that this is a predicate, right? Because although I quantified the variable k, so k is no longer a free variable, x is still a free variable, therefore it gives me a predicate. So, what does it then mean for odd x? Well, it would be the negation of this, but there is a better way of saying this. How does an odd number look like? Well, it's an even number plus 1. So there is a k. So rather than using the fact that odd is the negation of even, working with negative things is so hard. Negations are hard to understand. So we always try to get something positive. And this is a positive definition of what it means to be odd. Namely, you're a number of the form 2k plus 1. What does this mean? Well, take k, any number, 17. 2 times 17 is 34. And then plus 1 is 35. Okay? So that gives me an odd number. And every odd number I can generate this way. Because every odd number is one further than an even number. And every even number is a multiple of 2. So here we are. So given that we know what these predicates mean, we can now work out a little bit better what our supposition is. N is odd. So that means there is some k. I'm now using, if you want, universal instantiation. Existential instantiation, because in an instantiation statement says there is some k such that n is odd. Sorry, I'm pointing to the wrong one, right? I'm trying to put n is odd. So it's this one, right? Not that one. Existential instantiation of the predicate odd says that such that n, my variable was now, I called it n is 2k plus 1. Okay, is this helping me? Well, we have to show what we want. We need to know something about n squared. Well, now I have some form of n, so perhaps I can calculate n squared. What is n squared? Well, this is 2k plus 1 squared. I am lazy. I'm using the double product formula. A plus b squared is a squared plus 2ab plus b squared. That's the double product. That's why it's called this way. So 2k squared, that is 4k squared, plus the double product, 2k plus times 1 times 2, so 4k, plus 1 squared, 1. Okay. Now, you might already recognize that this is an odd number, and later we will talk much more about odd and even and all these things in our so-called modular arithmetic. That comes in a later chapter. But let's see what we want. To show that you're odd, you have to write it as a multiple of 2 plus 1. I have the plus 1 already, so let's factor out a 2 here. Can I do this? Yes, you can factor out a 2. 2 squared plus 2k plus 1. And now we see that there is some k. It satisfies, this is, if you want, existential generalization, right? There is a witness here to the fact that 2 times that number plus 1 is my n squared. So this gives me odd n squared. That is an existential generalization. I have a witness, namely this 2 squared plus 2k. I know exactly what it is. Well, yes and no, because I didn't know what k was. And that's because I didn't know what n was. You see, in general proofs, we don't have concrete objects. And that's why I was a bit hesitant using the word concrete all the way in the beginning of the movie. Okay, and that's how the proof works. And then if we're done with the proof, we like to say this by making a square little box. Some other symbols are used. The textbook, for some reason, uses a full a little triangle. You also might see this notation, QED. You might have heard of that. It means quod erat demonstrandum. What language is that? It's not Harry Potter language, demonstrandum, because, well, it sounds like it because that is based on Latin. So quod, that, erat, had to be, demonstrandum, demonstrated. That had to be demonstrated. Okay, that's what had to be demonstrated. What we wanted to show in English. Okay, so I'll do one quickly. We show that if m and n are perfect squares, then so is m times n. So what is a perfect square here? Perfect square of x. What does that mean? Well, it means it's a square. So it means there is a y such that x is y squared. Okay? So here, again, our official statement should be, for all x and y, perfect square x and perfect, so I hate square y, imply, sorry, I have to write it here, perfect square xy product. Okay, that's the official version of our statement. Now, how you do this? A proof. So let m n be perfect squares. So you notice the usage of the word let here. It means it is exactly what universal instantiation is. Let us take an arbitrary m and n. Let us take somebody. I'm not going to say none of us is committing to any particular one, but just to the fact that it is one. Let m and n be perfect squares. So to show mn is a perfect square. Okay, so again we have to actually analyze this perfect square business here, right? So we know that m is a perfect square by existential instantiation. We know there is an a such there is for some a m is a square. That is, so notice what I'm doing, right? This is an existential quantifier now. So our statement has become, sorry, the statement that we have is perfect square m. That is a proposition, because m is no longer a variable, because I said let m be a perfect square. So it is one particular perfect square. And therefore it's no longer a variable. Variable means that it could be anything. It is now a particular chosen one. Which one I don't know. Perfect square m. So this is now a predicate, and that predicate, so we have now this is the same as there is a y. M is y square. Okay, that is just rewriting this statement for plugging in m for x. Now I want to use universal instantiation, existential instantiation, saying, well, this says that there is an a, for some a, m is a square. I'm going to do the same for n. I'm going to skip the details now. So there is, for some b, we have n is b square. And now the proof is very simple. Remember, we want to do something about mn. We have now, that the whole point is getting a new form of my numbers so that I can do at least some arithmetic, some calculations. Okay, a square times b square. Now I want to prove this is a perfect square. That means I have to exhibit it as a perfect square, and that is by one of the rules of exponentiation, ab square. And this now tells me that from this, by existential generalization, I have an ab for which is true. That means there is a y such that mn equals y square, and this means exactly that mn is a perfect square. And so again, I'm done. Now, some of these I worked this out in really deep details, right? I kept every time saying existential instantiation and then existential generalization. So I didn't write it here. So existential generalization. Now, in most proofs, we don't even say this anymore. It's just understood that's what we're doing. Because phrases like let m be in, that's a universal generalization. For some, that's an existential instantiation, and so on and so forth. Okay, I'm going to leave it here, and so the next one will be on a rather strange way of proving things that's called proof by contradiction.